Section 2.4, Using Linear Models. Objective, to write linear equations that model real-world data to make predictions from linear models. Let's start with an example. A military jet descends at a rate of 5,000 meters per minute from an elevation of 20,000 meters. Write an equation to represent the jet's elevation as a function of time as it descends. Graph the equation to describe the line. Well, if we're going to graph this equation at the end, we know that we're going to have values that represent x and also y. And in our problem, we are given elevation as a start, and we know that it's descending at a rate of 5,000 meters per minute. Our equation is going to be the slope-intercept form of a graph. So y equals mx plus b. We have b, which is a y-intercept. That's the starting point. Our starting point in our graph is given by the elevation of the jet, which is going to be 20,000 meters. And I know the rate of change of that elevation, which will be our slope, our change of the y and the change of the x, which is going to be 5,000 meters. But here, recall that it is descending. Therefore, that is going to be a negative value for the coefficient of my x. And that gives me my equation, y equals a negative 5,000 x plus 20,000. X will be my minutes, and y will represent my elevation. And that will depend on the number of minutes I'm going to calculate. I already have a graph that is set up for my y values, the elevation, in terms of thousands. Each line is going to be 2,000 feet, 2,000, 4,000, 6,000, 8,000, 10,000, 12,000, and so on. For minutes, each line is going to represent 1 minute, 1, 2, 3, 4, 5, 6, and so on. Let's graph this equation by setting up an XY table. Here, let's start out with our initial minutes of 0, which was initiated in our problem. So when we substitute in 0 times a negative 5,000 is 0 plus 20,000 gives us our y-intercept of 0, 20,000. After 1 minute, we substitute in. That's going to give us 1 times a negative 5,000. A negative 5,000 plus 20,000 gives us 15,000. After 2 minutes, we can see we're going to have a negative 5,000 times 2, which is going to give us a negative 10,000. Adding to 20,000 gives us 10,000. At 3, when we substitute in, that'll give us 5,000. And at 4 minutes, that will give us 0. When I graph 0, 20,000, 1 minute, 15,000, 2 minutes, 10,000, 3 minutes, 5,000, and 4 minutes would be 0 elevation. Then I connect. And this line describes the elevation as a function of time. So, determining the number of minutes, I can make an independent time choice and substitute in and estimate the elevation of that jet. Another example. A spring has a length of 6 centimeters when a 30-gram disc is attached to the spring. Therefore, it drops down below the x-axis. Each time we remove a gram from the disc, the spring recoils, or in other words, it gets shorter, by a length of 0.10 centimeters. Write an equation for the length of y of the spring as a function of mass x of the attached weight. Graph the equation and describe the graph. Again, knowing we have to graph, we're going to have a value for the x and y. Let's again use our slope-intercept formula, which is y equals mx plus b. B is our y-intercept, and we know that is our initiating starting point. And on our problem, 6 centimeters is our starting point. But recall that when I hang a 30-gram weight on that spring, it will drop below our x-axis. Therefore, that y-intercept is actually going to be at a -6. I also know that I have a change for my slope to be at a rate of 0.10 centimeters for each amount of gram I remove from that spring. So that's going to be 0.10x minus 6, and that's going to be my value for y. Now, what I'm going to do is identify my x to be the number of grams, and y is the length of the spring. So all I need to do is to create a table to represent those values, x, y. If I don't remove any weight, I am at 30 grams, and my length of spring is going to be 0 times 0.10, which is 0 minus 6 is a minus 6 units below my x-axis. 1, when I keep substituting, 1 times 0.1 minus 6 is going to give me 5.9, and that will be negative. And 2 times 0.1 will be 0.2, negative 5.8 for 3, negative 5.7, and so on. Now, all I need to do is to graph my table. 0 grams removed, the length is 6. 1 gram removed, 5.9. 2 grams removed, 5.8. 3 grams removed, 5.7. Let's connect our points. And this graph represents the length of y of the spring as a function of mass x, which is the weight in grams. Our next slide has a continuation problem. How many grams would need to be removed to achieve a spring length of 4.7? Well, if I go back and estimate 4.7 to be about here, I can go till I get to about this location. I know this isn't on my graph, but I could estimate that to be close to 13 grams removed. I also could get an exact answer by substituting 4.7 into y and solving for x. But from my graph, I'm going to approximate 13 grams. Our next slide has the definition of a scatter plot. A graph that relates two different sets of data by plotting the data as a set of ordered pairs. You can use a scatter plot to determine a relationship between the data sets. Here we have the idea of correlation. The idea of correlation is whether it is positive and negative, and also whether the data can be seen to form some sort of a line. So if I take a look at this set of data here, some of it looks like it actually can form a line. Here, it looks like it can form a line even though the data is not very tight together. Also, if it did form a line, it would be increasing from left to right. Therefore, if it's increasing from left to right, it would be a positive correlation. And even though it's not very tight together, it does look like it's forming a line, but it would be called a weak correlation because it's not tightly knit. Here, the data is very close together, very tight. Also, it is increasing from left to right, so that tells me that it's still a positive correlation, but since the data is very tight together, and it looks like it's forming a line, very tightly knit, that would be a strong correlation between the set of data. Here, it looks like my data is decreasing from left to right, therefore that would be a negative correlation because it's decreasing, and the data is not very close together, but it still looks like it's forming some sort of line here, therefore it is a weak correlation. On the next set of data, again, my data is decreasing from left to right, and I know that that represents a negative correlation because of the decrease from left to right, but it's very tightly packed together to form that line. Therefore, that would be a strong correlation and also a negative correlation. Here, my data is scattered throughout my graph, It doesn't look like I can create any sort of line in any direction being positive or negative. Therefore, this is no correlation between the sets of data. Our next slide has a definition for a trend line, a line that approximates the relationship between the data sets of a scatter plot. You can use a trend line to make predictions. What they're trying to do is determine what set of points actually best describes a line here. If I would pick these 2 points to connect, that would describe the data, nor would these 3 or these 2 set of points. But what I want to do is select a set of points that best fits this set of data exactly. In other words, a line that most points cluster around. To me, it would most cluster around this point and probably this point. That way the data is very closely knit to that line, and that would be the best representation for this set of data. Here, the best representation for the set of data could be these points. And I selected this one and probably closer to this one. When you do this, it is more of a visual aspect of the person actually doing it rather than mathematical. We can get very, very close to getting the information we want, but it won't be exact because it could approximate from person to person. There is a way of getting the exact line of best fit here, and it's called regression analysis, but we're not going to cover that in this section. Let's look at an example for a trend line. The chart below shows the development costs for computers and computer equipment in general. Plot the data where X represents the year and Y represent the cost. Determine if there is a trend line. If so, draw a line of fit and determine its equation. Here, we're given the year, and I have 2000, which is represented on the origin, and then I have 2001, 2002, 2003, and so forth. Dollar amount is on the Y. That's at $50 all the way up to $85 going by increments of 5. I've plotted the data. Now I just have to determine which 2 points I want to select to create my line of fit. I'm going to decide the second point, that is the point at 2002, and the final point at 2005. Given those 2 points is 2, 68.9, and 5, 51.9. Using those 2 points from the previous slide, I've created most of the work to find that equation. Here I labeled my points x1, y1, x2, y2. Substituted in my slope formula, which is y2 minus y1 over x2 minus x1. When I did that, I got a simplified negative 17/3, which makes sense because my line is decreasing, therefore my slope is negative. I substitute my ordered pair into my point slope formula, which is y minus y1 equals m times x minus x1. Either point will do, but I will use my subset of x1, y1. When I substitute in, I get y minus 68.9 equals a negative 17/3, x minus 2. This equation represents my trend line for this example. The trend lines can be a little bit different because we get to choose the 2 points to create that trend line. Just try to be as close as possible. Let's look at an example for a trend line. Below is a chart that represents the cost of crude oil price per barrel from 1950 to 1959. Let X represent the year and Y represent the cost. Plot the data on a graph. Decide whether a linear model is reasonable, and if so, draw a trend line and write an equation of the line. Here's our chart. The x-axis is going to represent our year. So here we have 1950, 1951, 2, 3, 4, and 5. And this is our dollar value per barrel. And this is 275, 280, 285, all the way to 315. I plotted the data points and see that they do cluster in a positive correlation. So therefore, I think I can create a trend line. Or in other words, I can pick 2 points out, draw a line between those 2 points that most of the data clusters around. So this is your choice to do this. This can be your choice and answers can vary. Again, I've already discussed that there is a way to actually model this mathematically. So what 2 points did I pick? I picked 1951, 277, and I've also picked 1957, and that would be 314. So year 1, $2.77, and year 7, $3.14. Now, I need to create an equation using these 2 points. To do this, I need to find my slope. Recall my slope is y2 minus y1 over x2 minus x1. I'm going to let this be x sub 2, y sub 2, x sub 1, y sub 1. Substituting in, I'm going to get 277 minus 314 over 1 minus 7. When I simplify this, I'm going to get 277 minus 314, which is going to give me 37 cents over a negative 6. When I simplify, I'm going to get 0.06. That's going to be my slope. Now, all I need to do is to plug one of these points into the point slope formula with our slope. Recall that our point slope formula is y minus y1 equals m times x minus x1. When I substitute y minus, since I have y1, I will use my y1 ordered pair, but it doesn't matter which one you use. I'm going to get y minus 3.14 equals 0.06 times x minus 7. And that is the equation that represents my trend line on this slide.